Hi everyone, and welcome to another technical deep dive for data scientists and machine learning practitioners who want to boost their technical skills. As data scientists, you know that you spend a lot of time combing through data sources, generating insight, and experimenting with models, but while Python is a powerful language and has a really vast ecosystem, sometimes it's kind of hard to do all of these things when data size is huge, and that makes your computational complexity much higher. In this presentation, Richter, senior data scientist at Saturn Cloud, will give an overview of current landscape for accelerating data science in Python. Enjoy.
All right, well, thank you everybody for coming. Thank you for Data Science Salon for putting together this virtual conference and making it a good experience for everybody. This talk is all about making data science faster with Python. And we'll talk about hardware and software, a little heavier on the software side. The key here is that we're not going to go super in depth into any particular tool. It's just for you to get information to do your own research based on your needs and your organization. It's specifically targeted for data scientists and data science teams. Tool sets are slightly different for data engineers or DevOps or other groups. And then it's particularly important when thinking about enterprise adoption. So if you're kind of solo and tinkering with things, you might try some things. But if you want to implement something into your organization, there are a lot of considerations. And if you want to follow along, I have a bunch of links throughout the slides and resources, so you can download them from the console for the talk. Quick about me. I'm a senior data scientist at Saturn Cloud. We'll go into who and what we do there. I also organize the PyData Miami conference, but my main work is just to make sure that data scientists can provide value to their organizations as quickly as possible with the tools that they know. And then if they need to learn tools, we'll give them easy access to be able to do that. And if you want to reach out to me on Twitter or email, you can check it out there. Just a quick about Saturn Cloud. We're a data science platform built for the PyData ecosystem. So we have a major focus on Dask and Rapids for accelerating data science, and those are two of the tools we're going to talk about today. So full disclaimer that that's part of the company that I work on. We're working out kind of enterprise solutions for them. But I'm going to do my best to give a fair shake about all the tools that we review. So there might be a little bias, but kind of any review like this that you might see is going to have a little bit of bias, but I'm at least telling you up front what mine is. So we'll just start off with just like a quick level setting of the quote unquote like traditional data science landscape with Python. These are the tools that data scientists are used to using, super mature, tried and true things that you're used to using on your laptop or your workstation, things like pandas, numpy, scikit-learn. The challenge here is that a lot of these tools were built for single core in-memory work. So if your data set's larger than memory, you're kind of stuck, or if you have a lot of computations, it might take a long time. So that's kind of where we're starting from, assuming that there is some sort of pipeline or workload in these kind of single core in RAM tools. And then we want to accelerate those to work with bigger data sets or more intensive compute. And that's really where the focus of this talk is going to be. How do we take that stuff that we're kind of used to writing and then with the least friction kind of accelerate that? And so I only have one slide on hardware because it's a little bit simpler than the software landscape. The main thing here is that I'm just trying to convince you to use the cloud. So a typical workstation, you might have, up to 64 gigs of RAM, maybe typically a lot less, like 16 or 32. And then maybe you have 4 cores, 8 cores, and maybe you have a GPU. So the challenge with these, workstations, there's an upfront cost. You might have to pay a couple $1,000s to get them. And then when new hardware comes around, it's very expensive to upgrade because you have to pay that $2,000-3,000 again. With the cloud, you can get machines that have like over a terabyte of RAM, whether it's on AWS, Azure, or GCP. You can get hundreds of cores and even multiple GPUs where you only pay by the hour or by the second. And if you need more hardware, let's say you have a machine with 60 gigs of RAM, you run out, you can get another one with 100 just in a few minutes by swapping the machines. And then when you go to doing cluster computing, which is where we're going to focus on for a lot of this acceleration on the software side, the cloud makes that really easy. There's a lot of tools for that. And you can get thousands of these machines that maybe even have a terabyte of RAM. So the scale there is kind of just like really, really big. And when we're talking about hardware for accelerated data scientists, you really should live in the cloud. So the main focus of this talk is really going to be on the software and specifically for open source data science tools, particularly around accelerating data science. So how can we kind of take things that we do and kind of make it faster, work with larger data sets? This isn't an exhaustive list. This is kind of based on my experience and opinion. But these are some things that you might want to consider when you're adopting an open source tool for your enterprise or for your work. Origin is interesting because while the projects can change and mature over time, the origin story of the project is important because that's kind of all about the problem that it initially was created to solve and the community that it was kind of working with to do that. So it's a good point of information, though again, things can change over time. But that leads a little bit towards community and maturity, is that really just like, how old is it? How many people use it? Are bugs fixed regularly? How often are there new releases? That's something to consider to make sure that, if you run into problems, they'll be addressed. But also thinking about, if you run into problems, you're probably the best person suited to fixing that problem because you know exactly how to reproduce it. So contributing is all about, is the tool built in, is the package built with tools that you know? So like if you're a Python data scientist, is the library written in Python? So if you need to fix something, can you do that? Because if it's written in Java or Scala, maybe you can't do that very easily. Native support is all about, what does the library do like out of the box? And those, just like, does it do data frames? Does it do arrays? Stuff like that. And then ecosystem is when it doesn't do things out of the box, what other tools are built up around it or on top of it that do the things that you might need. And that's a really important consideration, because if there's a bunch of packages built on top of another one, that means that package is really sticky and it's expected to be stable because a lot of other packages kind of depend on it. So that's kind of a good sign. And then if compatibility is more of like, if it doesn't do the thing that you want and there's another package that does, how easily can you pair those two libraries together and interact between them? And then deployment is all about, how do I actually start using the tool? Is it really hard? Is it just a pip install, or is it really hard to configure? Do you have to like set up a bunch of hardware and infrastructure stuff? All those considerations. And then here on the other side, this is really all about the out of the box, like native support, is what type of workloads does the library support natively? And so this is, again, not an exhaustive list, but these are some of the key ones that data scientists work with. So we're talking about arrays, data frames, machine learning, and then kind of like arbitrary workloads. So with a review like this, you might expect a table with check marks, like with all of these things on the x-axis and then all the tools on the y-axis. I'm purposefully not doing that because there are varying levels of support. So if you see like a checkbox or an X, you might think it's completely supported or not supported, but it's a little fuzzier than that. And also that these projects evolve quickly, and there may be things that I don't know about, because so I don't want to put like a specific like table, but I'll talk about all these different considerations, and then I'll think about these different workloads and kind of give recommendations on each and ways that you might want to do some more research. So as far as the software landscape, I'm going to throw a bunch of logos at you. And the idea here is that you'll just be able to see them, hear how I talk about them, and then do your own research on them later. But we'll start off with kind of the PyData world, as I'm calling it, as we kind of introduced already. This is the stuff that data scientists are used to using, the tried and true packages, usually on like a single core and on your laptop or your workstation. It's really important, though, to mention this other side of kind of a parallel world that was developing pretty much at the same time, like over the last 10 years, is this big data world. So this is really kicked off by Hadoop and kind of that distributed computing paradigms, more focused really on like the data engineering, data warehouse world. So the communities that use these tools are very different, sometimes very different than the PyData communities, which are more scientific computing and data science. But some of the popular packages I've listed there, a key one we're going to talk about is Apache Spark, because it, while it was born kind of in the Hadoop world, it does have a lot of things that data scientists might use it for. But the bottom here is really kind of like this new world of combining big data and the Python PyData ecosystem. So it's doing your scientific computing stuff on large data sets or with really complex compute. And we'll go into all of these packages. I'll say the most, just to start off with, the most mature and big players kind of in this space as far as distributed data science are Spark and Dask. They're definitely the most mature. And then we'll talk about some of these other packages too. So I'll go into each one of these, and then afterwards I'll go into the workloads and then kind of give considerations that way. So we'll start with each and then kind of pivot that. So Spark, like I mentioned, is kind of born out of the Hadoop kind of big data world. It's a distributed computing platform, which means a cluster computing platform built upon the MapReduce paradigm. So it is fairly old, probably the oldest package we're talking about here, made around 2010 out of UC Berkeley. It's built in Scala, which means it runs in the JVM, though it does have an API for Python. It is a very mature community, like I said, especially in the big data engineering worlds. That community uses Spark heavily. Things that data scientists might use Spark for are the data frame API that it has, and then there's some machine learning there as well, probably the two biggest things. One thing to note, though, is that Spark, it's built in Scala, it has Python API, but it's like a completely different project. So the rest of the projects I'm going to talk about are more integrated into the PyData world, whereas with Spark, you're probably going to have to rewrite all of your code. Like let's say you have scikit-learn code and pandas code, you're probably going to have to rewrite it into Spark. So because Spark was born in the Hadoop world, it integrates well with that ecosystem. So tools that other people might use there is like HBase, Hive, Cassandra, stuff like that. There is some Python integration. It's kind of limited because you're really working with user-defined functions that operate like on a data frame. So you're going to say you can write some arbitrary Python code and then apply that with a UDF, but then that still kind of gets pushed through the whole like Scala engine. And then the one thing here is that Spark is generally a cluster computing tool. People really almost always just use it on clusters. The deployment can be complex to set up, and you usually have to tune your jobs a lot, like setting memory settings and different things. But if you want to check out Spark more, you can click that link there. All right, the next one is Dask. So Dask was made around 2015, created at Anaconda. So Anaconda at the time, I think it was Continuum Analytics, but they're really like the forefront of the open source Python data science, scientific computing ecosystem. And it's also a distributed computing or cluster computing framework. But the key here is that it's built around dynamic task scheduling. So it's very, very flexible. And the goal of the Dask package is really to be a, flexible parallel computing Python platform for the Python ecosystem. So it's compatible with a lot of packages. So generally, if you do something in Python, you can probably make it faster with Dask pretty easily. And by easily, I mean minimal code rewrites because it's kind of compatible with this ecosystem already. So it's built in Python and there's a Python API. Like I said, it's very mature in the scientific computing communities. A lot of like geosciences and a lot of other types of scientific computing communities use it a lot. It's parallelizable from like low level, like arbitrary functions. And then it does have high level libraries for data frames, arrays, and machine learning. And it integrates really well with pandas, NumPy, and scikit-learn. It'll run on your laptop, so it'll take advantage of all the cores on your laptop really easily. And then that same code will scale to clusters with pretty minimal configuration that you would need when you're trying to run jobs. So, and it has a lot of libraries built on top of it. So if you go to this dask.org page and scroll down, you'll see the Powered by Dask section, which has a lot of packages kind of in this ecosystem. So, all right. Next one is Ray. So Ray is a little bit newer than Dask. It actually came out of the same lab at UC Berkeley that created Spark. They changed names. But it's also a distributed computing platform built around task scheduling. It's built in a mix of like C++ and Python, has APIs for Python and Java. The low-level task library, at the face of it, is actually very similar to Dask. And there's a pretty good GitHub thread where the founders of Dask and Ray actually talk about the differences, particularly around the details and mechanics of the task scheduling is where they differ. And then the high-level libraries are very different. Ray was built focusing a lot on reinforcement learning, deep learning, and hyperparameter tuning for deep learning. So that's kind of where it's kind of oriented as a package, though the low-level task library can kind of parallelize anything that you want. Same as Dask, it'll run on a laptop and scales to clusters. One note is that if you're a Windows user, it's still an alpha. It originally didn't support Windows, and so the Windows support is an alpha. It might not completely work, so just a consideration as well for that. So this other package is very different than the first three that we talked about. Spark, Dask, and Ray are all about distributed parallel computing and getting performance gains by kind of scaling out on a cluster. Rapids is something that gets performance gains by pushing your computations to a GPU. So data scientists might be used to GPUs for doing like deep learning with PyTorch or TensorFlow, but Rapids actually does all of the non-deep learning stuff that you would normally do with like pandas, NumPy, scikit-learn, but on the GPU. So it's a much newer package, but there's a lot of support from NVIDIA. It's completely open source, but NVIDIA does employ a lot of engineers and developers to maintain the package, and there are other developers from other organizations also working with it. So if it doesn't do something right away, it's probably going to get supported very soon. So it's built in a lot of C++ because it works with CUDA, but then there's a Python API there. And it has a lot of packages that it supports like natively. So we're talking data frames, arrays, machine learnings, like graph streaming. There's a whole bunch of stuff. If you go to the Rapids page, you can kind of see all the different kind of workloads that it supports. And similar to Dask, it integrates really well with the Python ecosystem. So the goal is to kind of match the Pandas API and scikit-learn APIs and interact with them as well. And what's really cool is that, you know, a lot of times you might be limited by GPU RAM because GPU RAM is a lot less than what you would have on main memory in a computer, but you can actually scale to clusters of machines with GPUs, and Rapids actually uses Dask internally for that. Okay, so now kind of flipping this a little bit, thinking about workloads. Probably the most crowded area here is data frames. And when you think about data frames, Pandas is kind of like the source of truth for what a data frame API should look like, right? So all of the packages listed here match the Pandas API, except for the first one, the PySpark data frame. So like I said, PySpark, the Spark is like a different package. So if you had a bunch of Pandas code, you might need to rewrite it. That being said, the third one down there, Koalas, is a package built on top of Spark that is meant to match the Pandas API. So you would write Pandas code and then it would actually execute at Spark on the back end. But you might be limited, right? Because if something isn't working, you're going to get like those Scala Java errors. And then if you need to do something more than what's supported in the Pandas API, you're going to have to drop back to the PySpark data frame API. So Dask data frame, we kind of talked about already. The Modin is a pretty cool package. And so what Modin does is their goal is you would be able to just replace one line. So instead of import pandas as PD, you would import modin.pandas as PD, and then all of your code would be distributed to a cluster based on the backend that you choose. So it actually is compatible with Ray or Dask as the backend, but the goal there is for like Pandas API completeness. VAX is actually not really a distributed computing platform. It's more of a lazy evaluation and out of core type stuff. Again, matching a Pandas API. So if you're using a single machine or a laptop or a single workstation, VAX is trying to load data sets and do things on data sets that are larger than that machine's memory. And then Rapids is again the GPU one, and their data frame package is called cuDF. And again, it matches the Pandas API. So if you're only doing data frames, like only strictly doing data frames, you can try VAX or Modin because those are going to be like closest to the Pandas API. But you know, you're probably going to have to do a little bit more. So you'll likely need a larger ecosystem, something like Dask or Spark, because you'll want to do some other things too. Multidimensional arrays is a little bit simpler. With Spark, just off the bat, the programming model is just not really suited for doing multidimensional arrays. And then Dask does have a high-level interface for arrays that kind of wrap NumPy arrays in general. And then Xarray is a package built on top of that that adds labeling to it. Ray is possible, like from the low level, you can kind of distribute it, but there's not a high level API. And then CuPy is actually a GPU's CUDA accelerated, basically it's NumPy on a GPU. It's actually not part of Rapids, but Rapids uses it heavily like in their other packages. So. And as far as machine learning, there's a lot here, and I definitely encourage you to go and do your research and see which algorithms and everything are supported. But the quick note of this is, if you have a scikit-learn model that takes a long time to train, you're probably going to want to try Dask or Rapids because they match the scikit-learn API, and you can extend it pretty easily either to a cluster with Dask or switch it to running on a GPU with Rapids. If you have a small model and you're just running it training it a bunch of times with different hyperparameters, you could try Ray or Dask. They both have kind of built-in scikit-learn capable or scikit-learn compatible hyperparameter tuning. And then if you wanted to distribute deep learning training, like TensorFlow, PyTorch stuff, you probably want to look at Ray. And then with PySpark, again, you'd have to kind of rewrite all of your scikit-learn code to be in that machine learning world. PySpark doesn't do deep learning kind of natively either. So the last thing I want to kind of talk about is this kind of unofficial guide to accelerating Python. So don't hold me to this, but this is generally the way that you would kind of want to approach this stuff. You want to use your traditional PyData tools on your laptop until it's kind of not possible, or it doesn't work. Then you can actually try a lot of these packages on your laptop or your workstation. So the packages that I've listed here, while a lot of them are cluster packages, will actually work very well with a multiple cores on your machine, and then you can try Rapids if you have a GPU. So if that doesn't pan out, then just get a gigantic machine on the cloud. Get a machine with 500 gigs of RAM. Use the same tools that I just listed there. It would probably work out well. And then if that doesn't work, then you go to a cluster. Your software kind of world is a little bit limited. You would want to think about just a couple packages there if you're using a cluster. And the last consideration is that you can use the best tool for your workloads. Like if you have a small data set and a lot of machine learning, you can use pandas just as it is, but then use Dask or Rapids for the machine learning. Or if you have a large data set and then you just need to sample it, you can use Spark or Dask for processing the data and then do like a single node scikit-learn situation there. So that's kind of the idea, but this is kind of like the stages that you would want to go through. And here's a bunch of resources. Like I said, go ahead and download the slides from the console in the resources area. You can check out a lot of these videos and articles. And then Saturn is just, we have a booth in the expo hall, go and the virtual expo hall, go and check us out. We kind of enable a lot of this kind of accelerated data science stuff. So with that, thank you very much.
I hope you enjoyed this presentation by Aaron Richter, Senior Data Scientist at Saturn Cloud. If you'd like to learn more from technical leaders, check out the technical track here at the Data Science Salon YouTube channel.